Interestingly enough, mathematics is the only field of endeavor in the sciences where it is reasonable to say that I can prove something. In chemistry, physics, psychology, history, the evidence tends to support. We use statistical methods. We don't actually ever prove something. This is it. But in order to do that, we have to follow our deductive rules of inference and our formal logical setups. So my goal, when I talk about a mathematical proof, is really to start with the idea of a formal proof. But a formal proof is a series of valid arguments. That are designed to arrive at some result. I believe one of the series of arguments you were asked to demonstrate in the homework was to end up showing it rained, right? This big long set of, I use this preposition and this thing, and then I use all my rules of inferences, it rained. Not one of the homework problems. So this is going to be a major pain in the ass. If I sit down and write this using nothing but the rules of inference and examples that we have, this is going to take forever. And that's just not worth it. So instead of using formal proof, we'll spend a lot of time in informal proof, which still keeps the rules of inference, but it doesn't require me to write them in that restrictive formal notation. But in order for me to do an informal proof, I need a little bit of vocabulary here. I need a statement I can show to be true. A theorem is a statement that I can demonstrate to be true. That demonstration is called a proof, but it's just a sequence of arguments that create this demonstration. Now, the word theorem itself is usually reserved for grand mathematical ideas. You've heard the word theorem before. We used it in calculus, the intermediate value theorem, the mean value theorem, Rolle's theorem. These are all statements for which I can write an argument that demonstrates that this is true. You will sometimes see propositions Well, wait a minute, I use that in my definitions of logic, right? I can only talk in propositions. But a proposition is a smaller true thing or claim. These are like theorems light. I still want to prove them when I think about mathematics, but they're not as deep or as involved. Sometimes I'll need to prove something on the way to proving a bigger result. And that sort of helper result is called a lemma. So my goal is to write down a theorem and to then write down the proof for that theorem in a way that convinces you that what I've said is not bullshit. To do that, I need to have a set of common assumptions. I need to know that we're working from the same playbook. So the set of assumptions I use are called axioms or postulates. And that's the base assumptions for the universe I'm working in. These are the ground rules. Now, in most of what we are doing, the ground rules are the long established principles of arithmetic or algebra or set theory. A lot of these have formal names, the names of the people who came up with these rules. For example, most people who study calculus work from the set of rules created by a guy by the name of Peano, Peano. A lot of people work according to Zermelo and Frankel when they talk about sets. But they're usually named after the people they wrote the book that they first showed up in. 99.9% of the time, I'm not going to do any weird crap. And the axioms and postulates I'm going to work from are things you've already seen. Almost all theorems that I will write down are universally quantified statements. For every continuous function where f of a and f of b are different, that's the start of the intermediate value theorem. But it starts with a universal statement for every continuous function that has different endpoints. If I'm talking about numbers, I might not explicitly say for all x, for all y. I might start with something like, hey, two even numbers. I'm talking about any two even numbers, that's universally quantified. Two other ideas of notes. A corollary is a consequence of a theorem. It might be a special case, it might be a particular example, but it's a consequence, usually a simple consequence of a theorem. And if I haven't actually proved my thing yet, then it's not a theorem, it's a conjecture. There are a large number of very famous conjectures. I'll talk about a couple of them as we go on. But a conjecture simply means I don't have a proof yet. I might not ever have a proof. I might eventually show that the statement is not true. But at the moment, we think it's true. Excuse me. Almost all of this language descends from our language informal proof. So I'm going to keep trying to use this language as much as I can. Questions? So how do I write a proof? I need a theorem as a place to start. So here is my theorem. Now I am going to make my life really easy. I am working in regular, ordinary arithmetic. I am working with numbers, whole numbers, integers, under the rules of arithmetic you all know and hopefully love. I hope. So, my theorem is that the square of an odd number is also odd. That's a universally quantified statement. And it's even more than that, it's a conditional statement. What is the if part of this statement? I need to at least have a translation into rough formal language so I can try and figure out what I'm actually trying to show. There's an if-then statement hiding in this sentence. How do I read the if-then? Blake?
If the square of the number is odd, then if the number is odd, then the square is also odd.
I got to be careful about which way it's going to go. If a number is odd, then its square will be odd. And then I can see where the universal quantifier comes in, right? Because I can pick any number. So let me write this sentence formally, just for the moment. For any number, which I named n, you can call it anything you want, n odd implies n squared odd. Okay. Okay. That's my formal-ish statement of my theorem. I need the axioms, the postulates, the definitions so that I know what these terms mean. How do you know if a number is odd? Evan? It can't be divided by 2. Well, 7.3 divided by 2 is 3.65. 9 divided by 2 is 4.5. So I think I need to be a little more precise.
It can't be divided into a whole number.
Aha. When I divide by 2, I don't get a whole number. As a matter of fact, I should be even more precise. The n in this question has to be itself a whole number, right? So I can't start with 4.5 or 3.7 or whatever the hell number I mentioned earlier. I have to start with a whole number, and then I have to divide it by 2, and I have to not get a remainder. If you take a whole number and you divide it by 2, what are the possible remainders? Either 1 or 0. So there's my way of defining it. A number is odd if when I divide it by 2, it'll have a remainder of 1. And a number is even if when I divide it by 2, it'll have a remainder of 0. I'm going to change my perspective. Instead of dividing, Let's think about multiplying. Definition. N is odd if there exists a k integer. The reason I used integer instead of whole number is because integer includes negative numbers with n is twice that thing with one left over. There's my remainder. So 9 is 2 times 4 with one more. 17 is 2 times 8 with one more. And n is even if there exists k integer with n equal to 2k plus 0. So now I have in my back pocket the ground rule definitions. This is what it means to be odd. This is what it means to be even. Now I can try and use this information to write a proof for my theorem. Okay. There are several different methods by which I can write a proof. The one that I'm going to start with is called a direct proof. Direct proof is really an informal version of modus ponens, of detachment, of if A, then B. Well, here's A. Now what do we do about B? P arrow Q, using the rules of inference. I'm trying to prove something about an if-then statement. The if in our case, n is odd. I want to end up with n squared being odd, right? So here's the deal. I'm going to start with the if, because that's the way detachment works, right? P arrow Q, here's P, let's end up at Q. Okay. Here's where I start. Suppose the n you give me is odd. An odd integer. That's where I'm starting, because that's what you told me was my theorem. If n is odd, then n squared is odd. So that's the P part. What's it mean to be odd? I wrote it down. But I'm going to use this version. It means that there is some k where n can be written as 2k plus 1. So, in your head, pick any odd number, whether it's positive or negative, doesn't matter. -7 is 2 times -4 plus 1. I got bigger than -8. 37 is 2 times 18 plus 1. The fact that I can tell you that n is odd means, in a detachment sense, there exists k integer with n equal 2k plus 1. That's just the definition. This is what happens in almost every proof. You apply the things you know about the object you are looking at. I know n is odd. I'm going to write down what that means. My goal is to look at n squared, right? So let's start looking at n squared. Then, n squared. Wait a minute, this is n, isn't it? So let's square that. Here's my favorite part. Regular ordinary algebra. Multiply that out. Colin? Now, I'm going to be a pain in the ass. That is odd. Sure it is. How do you know that that's an odd number? When my definition of odd means I can be written like this. I have to take this thing and write it like this. How can I rearrange what is currently down here at the bottom to be 2 something plus 1? Well, I got the plus 1. That's nice. So what if I take this and rearrange it so there's a 2 outside? What goes inside that set of parentheses? Aha! I factored out a 2, right? Now, what do I know about the number k? All I know about k is it's an integer. When you multiply an integer by 2, you get another integer. If it's positive, it stays positive. If it's negative, it stays negative. If it's 0, it stays 0. But that's still an integer. When you square an integer, it stays an integer because you're multiplying it by itself, right? When you multiply an integer, you get an integer. Then I'm multiplying by 2. Then I'm adding. When you add integers, don't you stay integers? This thing inside the parentheses, I don't know what it is, but I know this thing is some integer. Existential instantiation. I don't know what integer it is, but it's some integer, right? Let's give it a name. What do you want to call it? I've already used K and N and L. I need to use, say it, I. So we'll call it I. Capital or lowercase? Hey, wait a minute. N squared can be written as 2 times an integer plus 1. Isn't that the definition of being odd? Therefore, N squared is odd. Now, I just put a check mark at the end of that to say that is the result I wanted to end up with. This is my demonstration. This is a sequence of statements that demonstrates the truth of my statement. If you start with an odd number and you square it, you will end with an odd number. I did not do a single example. I did this in general principles, right? If I was really being a fancy dork about it, I would say, so I have demonstrated. And I would say it in fancy Latin. So if I want to say, so I have demonstrated, I would say, quod erat demonstratum. So it has been shown. And that's why people say QED at the end of a long argument. A lot of textbooks will actually write a little block and they'll shade it in. And you'll see this sort of block at the end of the proof. Hey, punk, I did it. I don't care what symbol you put at the end, but show me, hey, no, this is where I wanted to end up. Check, I knew I got to the right place. Do you see the detachment part going on here? I started with my hypothesis, my premise. I looked at my if then, I started with the left side and I worked my way to the right. And I got the conclusion I wanted. Questions? I will be one of the first people to tell you, I love direct proof. I go marching along my logical chain of arguments, bing, 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 and I end up where I wanted to end up. Love it. But that's not the only type of proof I can write. I'm working with the idea of odd and even numbers because we all really understand what those are. I'm trying not to pick something where I need this huge pile of background information for you to understand what I'm talking about. That's why, in spite of me starting with something like the intermediate value theorem as a discussion point, I'm not actually going to prove the intermediate value theorem because it's a pain in the ass to actually write a proof. There's a lot of underlying pieces of calculus that we didn't cover in a Calc 1 class. So it's not worth it. I want you to think about this one for a moment, and let's see how we would write a proof if we did a direct proof. If I were to do a direct proof, where would I start? Huh? Oh, hang on a second. Look at the statement of the theorem. N being odd is my conclusion, not my premise. Aha! If I actually want to start with thinking about what it means to be odd, I need to start with the 3n plus 2 part. Because that's my if. Right? If this is odd. So this is where I start. Suppose 3n plus 2 is odd. And then I will agree with you. Then I should say, okay, well, that means there exists an integer k with 3n plus 2 being equal to 2k plus 1. Because that's what it means to be odd. Now, my conclusion is about n, right? The conclusion of my theorem is about n. So what should I do with that expression? With this garbage? Yes, Adam. I should rearrange it to get n all alone because that'll tell me about n. Great. So I start by moving the 2 over there, and that means that 3n is 2k minus 1 because I subtracted 2. And then I have to divide, right? So I get n is 2k minus 1 over 3. Houston, we have a problem. It's not a big problem, but it is a legitimate problem. Because I want to know whether or not this thing is odd. And all I know about k is that k is an integer. Somebody pick a number, an integer. 2 times 4 minus 1 divided by 3 isn't even an integer. Off. So I have just reached a point in what I thought was going to be a proof. where I've run into a logical wall and I don't know how to proceed to get the conclusion I want. This is the problem with a direct proof. I only have my premises and hypotheses and the laws of inference to go by. So I do not believe I can get to the conclusion I want from here. That does not mean my conclusion is wrong. It just means that this quote unquote proof isn't sufficient. This didn't work. Well, shit. I need to try something else. Go back to the list of the rules of inference. What were some of the other rules of inference that dealt with if-then statements, just like our detachment rule does? We had other rules, didn't we? As a matter of fact, the very next one that we said would work kind of like detachment, just slightly differently, was called what? I switched them around and I worked them the other way. I put knots on them. What did we call that if-then statement? Our contrapositive. We had that contrapositive detachment. Okay, wait a second. If I want to show this is true, I want to show a statement that looks like this is true. This statement is equivalent to its contrapositive. So what if instead of trying to prove it this way, I try to prove this version? They mean the same thing, don't they? So if I were to look at this instead, that's equivalent to the statement I was just looking at. But this is backwards and negated. So instead of going from P to Q, I'm going from not Q to not P. I'm kind of doing this upside down and backwards. So I'll call this an indirect proof. Or proof by contraposition. Well, that title makes sense because I'm proving the contrapositive. Okay. So the first thing I need to do is I need to take the sentence we were trying to prove and rewrite it like this. So my original statement, I scroll back up my page and I see my original statement. Blake.
Would be n is odd if 3n plus 2. N is even if 3n plus 2 is odd.
N is even. That put the negation on the Q part. If
Is also.
is also even. Okay. I need to put the if on this part. So my new statement is now if n is even, then 3n plus 2 is even. See how I reversed where the if goes? Now, my goal is to prove this. This is now a direct proof of a new statement. So I'm going to do this proof. What's it mean for n to be even? Suppose n is even. Then what?
A integer with n equaling 0.
I don't even need to put a plus 0. If I'm adding 0, it doesn't even go there, right? Great. My goal is to look at 3n plus 2. But you just told me that n was this other thing, right? So put that in there. But 3 times 2k is 6k, right? That's even. But in order for me to show you that that's even, I need to write it in the even form, which means it needs to be 2 something with nothing left over. What's the something? Oh. And again, k is an integer. 3 is an integer, so when I multiply those together, it's still an integer. And when I add 1, that's still an integer. This is an integer. Call it, okay, Jolanta, you gave me I, I'm going to use j this time. Two j with nothing left over. Therefore, 3n plus 2 is even. This is the contrapositive of our original statement. And that means that a proof of the first statement, n being even means 3n plus 2 is even, is also a proof of this. So in one version of this proof, I went from P to Q. That's a direct proof. In this second version, I would go from not Q to not P, but it still proves if P then Q. One does it in the direction of the arrow, the other does it in contraposition to the arrow. Questions? Yes, Evan.
Are you just putting the arrows so it's easier to follow, or do we need to put those arrows in?
The one that goes from the equal sign to the equal sign? Up there? No, I could replace that with a word like so or thus but we really are using it like the if then, right? This is my if, then this is going to be true, right? So I'm using it in the same fashion as my if then statement. That's why I try to write it that way. but it's not a requirement. Yes, Sean?
So should we be able to know which one to use, or is it like a trial and error?
I wish there was an easy way to know. If there was an easy way to know, we'd be a lot better off. My reaction is I always try and start with direct proof because that's more straightforward. But quite frequently, one of the problems is I don't know which is going to have more options in it. Which one's going to give me an easier result? If there was a simple way to determine those, I would try and write that, chisel it in stone, and present it all to you like a tablet from on high. But I am absolutely, when it comes to knowing, should I do this by direct or indirect? And frequently, the only way to try and get a feel for it is to try a bunch of them and to read a bunch of them. So here is a case where I am going to stress that reading math, this one type, isn't a passive behavior. When you read a proof, you have to make sure that when they use an arrow or a symbol or a phrase, you know what they did. That you follow the argument they are providing. And if they jump over something, you need to understand what the hell they skipped. Sometimes they just skip algebra, right? Oh, from here to here, it's just algebra, therefore we end up with this result. But that algebra could be 6 or 7 lines of expanding and canceling and simplifying and all that jazz, and that's not always pleasant. But the more I read proofs, the more I will be able to say, I think this one kind of follows the same idea as that one. And there are categories of proofs, depending on what field of mathematics you're looking at. A lot of number theory proofs that deal with dividing and multiplying, they almost all use multiplying instead of dividing because multiplying is easier.
On the test, would you know which one?
I would hope so. Otherwise, I'd be like, oh, here, try this. You'll be there for an hour just working on that one problem. Wham, no, that's people. But I need to know which method is which, right? So direct proof, E to Q. Indirect means contrapositive. I almost always start by direct. And then if I run into a problem like we did in this example, I go, hey, wait a minute. I don't know what I'm going to say about this conclusion. Even then, it is fairly easy to end up somewhere and go, well, of course, and be wrong. One of the things I had to do as part of my PhD thesis was I had to show something was continuous. Continuity, right? For every epsilon, there exists a delta, the whole nine. I had to prove continuity. I didn't. I just said, of course, this is continuous. It's a translation. I'm just adding. It's continuous. I wrote that on page 6. There were 98 pages in my thesis. Everything beyond page 6 was wrong because it wasn't continuous. And I had to rewrite the entire thing for the next 3 months. I was a little pissed off because I'd given them chapter 1 like 6 months earlier, and they hadn't caught it until the day before I was supposed to give the talk. So I fixed it. It turns out not to be continuous, and I therefore made not continuity the center of my process rather than continuity. Took the whole paper on its head. I'm not going to do that sort of stuff to you. If I say you can prove this, then you can prove it. More questions? Remember our truth table for the arrow, vacuous and trivial proofs. Please notice the bottom 2 lines. The bottom 2 lines say that if you start with a false premise, the if-then statement is true, right? So I am going to define a propositional function for integers. If n is bigger than 1, then n squared is bigger than n. Now I can prove this in a lot of different ways. But what if I ask you, can you prove P of 1? Wait a minute. If I put 1 in there, what happens? Is 1 bigger than 1? That means this is false. There's nothing to prove, is there? Regardless of whether this part is true or false, the result is true. P of 1 is true vacuously. There's really no proof there. It's a vacuum. When you start with a false premise, your conditional statement is automatically true. On the other hand, take a look at these two. Those two both have Q being true. Yes? Whether P is true or not, Q is true. Here's another propositional function, P of n. If A and B are both positive numbers, and A is bigger than or equal to B, then A to the n is bigger than or equal to B to the n. And the variable I'm looking at is n. If I again ask you about, say, P of 0, what is A to the 0? What is B to the 0? Wait a minute. A to the 0 is 1, B to the 0 is 1. That means that A to the 0 is definitely bigger than or equal to B to the 0. Do I give a crap whether or not A is bigger than B? This is true. It has nothing to do with the hypothesis being true or false. The consequent is true regardless of the state of the hypothesis. This is a trivial proof, since this doesn't care about A bigger than or equal to B. This proof is true, but not vacuously this time. This proof is true trivial. Vacuous proofs and trivial proofs are important pieces of our arguments. There are other proofs, and there are lots of other methods by which we do proof, and that is where I will continue this on Wednesday. I will see you all then.